Okay, I think we can get started. Some folks still trickling in, but we want everyone to be able to have time to get to the booth crawl later, so let's kick it off. Welcome, everyone. We got ourselves the SIG Node intro and deep dive. Thank you, everyone, for joining in this early evening, very late afternoon session. My name is Peter. I'm a principal software engineer at Red Hat, and with me today we have Sergey, staff engineer at Google. And we're here to talk about SIG Node. So if you don't want to listen to that, too bad. So I'm going to start off giving a brief introduction. I kind of doubt that most people need an introduction to SIG Node in this space, but if anyone does, we don't want to leave you behind. So SIG Node, so Kubernetes Node in a nutshell. I came up with this, or rather, a very smart philosopher named me came up with this today, which is like SIG Node is kind of where infra begins and infra ends and compute begins. So Kubernetes is largely an infrastructure platform as well as also an API. But at some point, eventually, there's workloads that get created, and those workloads. The beginning of the creation of those workloads, I believe, really starts with SIG Node, where it translates the desired state of a pod and actually creates that into a pod that runs workloads. So we have a little diagram of some of the components, and we're going to talk into those into more detail. But the biggest one that we're going to start with is the kubelet. I feel like this is really the bread and butter of SIG Node. And the kubelet is an agent that runs on every Kubernetes node, unless you're using virtual kubelet. And it does a number of things, some of which, it registers itself, the node object with the API, as well as watches the state, its state, which it owns, which is largely pods. It can create static pods from files, as well as pulls pods from the API. And then it reconciles that state via the sync pod by actuating the requested pods from either of those sources. It also connects, to other plugins like CSI, DRA, and CRI. So CSI is a container storage interface, which is used for connecting storage resources like disks, and then DRA is for Dynamic Resource Allocation, which is around attaching next-generation devices. And then the CRI implementation is Container Runtime Interface, which is how the pods are actually run. And it's the main entry point and exit point for calls into the node. So if you've ever looked at a log, queried a log from the API, or you've ever execed into a container, that gets proxied through the kubelet. With all the available compute that it has access to, the kubelet then, does a number of things with these. It advertises these resources, and it, in some case, it applies limits as largely by proxy through the CRI, but as well as in some cases quotas and defaults. It is responsible for admission on the node. So when a pod, even if a pod is scheduled there, the kubelet is ultimately the entity that decides whether or not it's able to run that pod. And sometimes it denies things at admission if it's actually not able to and the schedule was wrong. It is responsible for allocating and deallocating resources, or responsible for telling other entities like the CRI or CSI whether to do those things. And it monitors resource usage and process health, collecting metrics and reporting those up through various pathways, and restarting the process if it fails, and collecting the logs and reporting those. It also supports for some of these resources over provisioning, but if we have some bad actors or a pod that's using too much memory, or sometimes it will also evict things, especially if it needs to pull in something more important. So in addition to the kubelet, we mentioned a couple of these processes, but real quick, we have CRI implementation, which is also often called the container runtime. I like to call it CRI implementation because there's also lower level container runtimes, and that's confusing, which speaks over CRI, which is a protocol, to the kubelet, which is actually responsible for pulling the images, creating the sandboxes, creating the containers. Ultimately, the CRI is like one of the dumbest servers in the world. It does everything that the kubelet wants it to do. So the kubelet is really the brains of the operation. There's also the node problem detector, which is an agent that is monitoring node conditions that SIG Node also owns. We work with CSI and CNI, even though they're owned by SIG Storage and SIG Networking, respectively, and their interfaces like Kubelet and CRI allow plugging in storage and networking. And then we also, in conjunction with working group device management and also sometimes other SIGs like scheduling, we also work on the DRA drivers as well as device plugins, allowing next-gen and other things to be attached into containers. So what's new in SIG Node? As if you've ever seen one of these presentations before, you'd know recently we've been a really productive SIG, and the answer to that has been and continues to be a lot is new in SIG Node. So we have 2 releases since the last update that I personally did. But I just want to call out, again, I did the numbers, I ran it. We have been the reigning KEP champ in all of Kubernetes since 1.30. Someone else can check that number, but I've been counting, and it's been pretty great. And we only lost to SIG API machinery by 1 KEP in 130, so or 129. So yeah, doing pretty great there. And some example of this is here's 26 KEPs that we merged in 134, and some highlights there is we have some new exciting work, some of which Sergey is going to talk a little bit about, the container restart rules to customize pod restart policy, and then a number of DRA things that we've been working in conjunction with SIG scheduling and working group device management. The biggest of which is in 134, we had a number of long-awaited GAs, one of which was DRA structure parameters, so that was really exciting, and really marks a milestone for DRA, as well as we ove forward memory swap to GA, which was also a lot of hard work and a lot of discussion around that, and a number of other smaller things, as well as we had integration between features, so we had the in-place update of pod resources and pod-level resource. Pod-level resources being specifying CPU or memory for at the pod level rather than at the container level, and then having the kubelet sort of populate it correctly. And that is now possible to have also in-place update happen too as well. In 135, similarly, a little bit, 4 fewer, but still we're holding records. We have a number of KEPs merged in 135 and a number of highlights there. Then exciting new pieces, like Sergey will also continue with the container restart rules to customize the pod restart policy. Went to alpha, as well as node declared features, which is a way for the kubelet to say, like, to heterogeneous versions between the API and the kubelet, like, hey, I support this feature, to allow your clusters to roll out features earlier than maybe they would otherwise be able to. We also have more DRA movement. I'm excited about partitionable devices moving forward into another alpha, as well as a number of others. We have also more long-awaited GAs. We've been doing a lot of GAing recently, which is good and makes sense because we've been doing a lot of KEPs generally. In-place update of pod resources was a huge one, made it to GA in 135, and so that's very exciting. It's been worked on for a long time. And so yes, lots of really exciting work happening. I also want to shout out, so some of the reason that we've had so much productivity lately is we have this new program called the KEP Wrangler. Sergey is going to mention a little bit later, but basically these are people who are volunteering to help in the sort of some of the process pieces of KEPs. It's very hard as a KEP author to keep up with all the dates and everything, so they're sort of responsible for helping out with these things and helping ushering the KEPs, making sure approvers are aware of deadlines that they have. I really want to call out Sriram. He's been doing a great job leading it in the 135 cycle, as well as all of our Wranglers. We would not be able to be doing so much without all of these folks' help, and if you want to help on 136, the application will be going out in probably a month or so. I also just want to announce a couple of deprecations, 2 version 1s of things that we've had for a long time. The first one being C Group version 1. We've announced the deprecation as of Kubernetes 135. So as of, you can still use it. You just have to turn a flag off, the failed C Group v1 flag. And we don't currently have plan to drop support for it, but we would love to. So move over to C Group v2 so we can move away from v1. And then also Containerd the 1 series of Containerd are deprecated as well. And this is pretty much in alignment with some of Containerd's upstream support as well. But starting in 136, the Kubelet will not start if it's using one of these lower versions. So also migrate to Containerd v2. So Cgroup v2, Containerd v2, super easy. And so in addition to all of those things, nothing, we also have all of this other stuff going on. So we we're continuing the SIG Node CI meeting, which is a great way to get introduced to the community and help triage bugs and issues, as well as help us stabilize our CI. We also have, we're continuing, involvement in the working group device management, even though structured parameters has finished. There's still more work to be done there, and that work is also constantly changing. We also have 2 new working groups, working group Node Lifecycle, which is to address the graceful node shutdown and eviction request problem, where we want to have a way to tell workloads on a node that it's time for them to leave, and wait for them to stop, but not wait too long. As well as we have the checkpoint restore working group, which is building off of the forensic checkpointing, which is only doing checkpointing, and it's a little annoying to do right now. So we'd like to build out an API for that, as well as add support for restore, and hopefully even add some integrations throughout the Kubernetes ecosystem to use those things. So that's that's like, as of last week, was codified as a working group. We also have the node readiness gates, which is a new Kubernetes SIG project that the SIG is sponsoring, which is a way to taint nodes that have not ready plugins, and we're to see if the community picks this up and if we can have this pattern be used broadly. And then, as everywhere else in the Kubernetes community, we're constantly looking for AI improvements. And Sergey is going to talk about a couple of things there, but we always are looking for ways to improve the behavior of serving and training on Kubernetes. And so now Sergey is going to give us a little bit more information about some of the things that we've been talking about.
1, 2, 1, 2. Check the microphone. Yeah, thank you, Peter. Yeah, 40 caps were tracked for 135, and 135 is few months of execution, maybe 3. And during these 3 months, we have 5 milestones. You need to go through all the 40 caps to see what's happening, whether they're on track, not on track. As you can see, only 22 of them made to release. So this other 20 will go to the next one, and you'll go through them over and over again. That's why rank lists are very important, but also all the community is very helpful. And this maintainer meetings that we have is like we go through introduction, and then we try to go into deep dive. That's why introduction is not covering all the work we're doing. So if you're doing some work and you surprised you haven't seen about it, talking about it like too much, it's not because we don't want to talk about it, it's just we don't have enough time. So yeah, thank you everybody. Today I wanted to go to deep dive about pod restart policy. So pod restart policy, historically, when Kubernetes just started, most pods were one container, and this one container was serving Nginx. So if you have this target audience, you probably don't need to worry too much about how it restarts, because it always restarts. It always needs to be alive. It can only be deleted when you don't need this node any longer or this pod any longer, and you deploy a new version. So workflow and lifecycle is pretty straightforward. And then somebody said, like, oh, we need to have jobs there as well. And naively implemented jobs API and job pods were just restart policy never, meaning that you run to completion and you're done, or restart policy on failure, meaning that we will try to start you, and then if you fail, we will retry you again. If you want to continue, if you exited with exit code 0, then we will complete you. So quite straightforward, but it quickly ran into many problems. And one of the biggest problems was support for sidecar containers. So the paradigm changed when there is a pod with restart policy never, and there is a sidecar, is a container inside this pod that's running to collect metrics, for instance. And if this container fails, pod is not failed. And if this container fails, you want to restart it because it's sidecar, it needs to run. And we've been thinking about how to implement it, how to express this fact, and we realized that sidecar is best expressed by the fact that it is restartable even when pod is not restartable. So again, like pod is bigger construct. There are multiple containers inside, and different containers do a different job. And this pod, containers that is not main container, that just collects metrics, we can restart it individually without affecting the whole pod. And we wanted sidecar containers for many years. We only got it in 2000. What was here? in 133 it was GA to count like a few releases before that. It's when we got sidecars. So 7 to 8 years of Kubernetes, we didn't have support for sidecars. And the reason for that wasn't that we didn't want it, it's just we didn't have enough priority to implement it, and we didn't have enough workloads that will justify it. And what happened at that time at HPC happened. We have many, many customers who needed better job API. They wanted Q. Q is a project starting with K. So all these things were implemented, and we also implemented sidecars. So sidecars as a concept was from the beginning of Kubernetes, but then the pressure of HPC workloads appearing on Kubernetes made us implement the restartable sidecars. So this is how sidecar implemented, and sidecars created this, like opened the door for us to put restart policy on individual containers. So now it's not true any longer that when pod has a restart policy never, nothing is restarting inside this pod. Yes, sidecar will be restarting, and it opened the door, and suddenly we have so many feature requests that some of them from a long past, some of them fresh. I didn't list feature requests here. I just wanted to indicate that like there were many of them, and they all wanted different behaviors of container lifecycle during pod execution. So many scenarios, like some people want to say like my main container here, if it crashes, kills the whole pod, and it wasn't expressible. Another thing was when my container terminates, restarts the whole container, including init containers. So it was many requests like that, and there were so many scenarios, so many edge cases, and we don't want to solve all the edge cases. We are like, maybe we can just give you some API, and you will do it yourself. So first thought was like, let's give you some API to Kubelet, so your container will talk to Kubelet and tell you what you want to do. And then you can tell, like, kill the container, terminate, like, complete the pod, kill another container. And some people were implementing it already. They were doing it through a CRI API. So they would run pod as a privileged pod, and container will be privileged. It will have access to CRI API, like container runtime API, and it will go against like Kubelet and like do something with other containers of this pod. It is crappy solution. It doesn't really work and scale, but it is a solution, and it actually desired by some people who wants to express very complex scenarios, but reviewing those scenarios and looking deeply in what we actually want to implement, we realize that the most important caps we want to implement is restart policy on individual containers. Like this tree is enough if they are in individual containers, and we wanted to some specialized actions on exit for containers. So I will go into details a little bit later, but those two scenarios were pretty important, and they enabled very critical scenarios. And again, we didn't have it for many years, for 11 now, and now we implementing it, and we implement it now because of the pressure of AI/ML workloads. Like we have many training jobs that running on expensive hardware, and those training jobs needs to have more control over how they run and how they restart. So again, pressure created, like scenario were forever, pressure created from the scenarios made Kubernetes change. So a little bit details. I don't have that much time. I will go a little quicker through that. You can read about all these caps in details and provided links. So first cap allows you to set a restart policy on individual containers. So now if you have any container, init container, sidecar, and regular container, excluding ephemeral containers, they not support to be restartable. You can set restart policy, but on top of restart policy, we also allow you to set some conditions, some restart rules, and these conditions will tell for specific exit codes apply different rules. And moreover, we have more rules than we have restart policies. Let me go into details. So you see this container here. It runs inside. This pod doesn't make any sense. So it just for educational purposes, like this is how API looks like. So this pod has a restart policy never. This pod has default restart policy is always. So restart policy is always, but what we can express here is that this nginx that runs inside it, I mean, as I said, it doesn't make sense, but like if this container exits with exit code 42, then it will be restarted. Any other exit code is terminal. So any other exit code, pod will be terminated. So next, yeah, that's a little bit more details on what kind of restart policies and restart rules we support. And then on top of restart action, we also in 135 introduce new restart action called restart all containers. So now what we want to express here is that if you have specific containers that is orchestrator of your pod, so it may be sidecars that knows how to talk to central command point, or it may be your main container. This container may say that if I terminate it, then restart the whole pod from scratch. And it's very useful. And in this case, we will even restart starting from init containers or the sidecars. So we will terminate all containers, but keep the sandbox. And in this sandbox, we will restart all the containers from scratch. And it's very handy for many scenarios. I think next slide is scenarios. No, next slide is example. Yeah, example is straightforward. Let me go to, OK, where are scenarios? Oh, those are scenarios, actually. Yeah, I thought I'm on a different slide. Yeah, so yeah, scenarios are quite interesting. So first, you can express the fact that some people have very heavy initialization, and this initialization will read some secrets from database or something, and they asked us, if my container terminated and crashed, I want to reread all the secrets and reinitialize everything. And there was no way to express it except move everything into the main container. And this is not a good solution, so we enabled this scenario that was with us for many years. Second scenario is more interesting. This scenario, one example of the scenario is gaming. We have many people who doing gaming servers, and imagine you have a pod that enables gamer to play their game on a mobile phone, and one instance of a execution is one session. So what we find out from these customers that if they use pod per session, they have so many pods, because sessions can be quite short, that Kubernetes cannot keep up with that. All the overhead of creating everything is too high. So what they wanted us to do is to say, if my session needs to restart inside the same container, so I want to reuse the whole execution flow, all the sandbox, all the mounts, all the connections, but I just want to restart my code, and I cannot clean it up myself because I run some third-party server or some something that I don't control, and this thing may make the container dirty. So I want to remove this container and create a new one on top of it. So this is a second scenario. And third scenario, that is main motivation factor that bumps the priority of everything a lot way higher is AI/ML training job execution. When we have a large job running the training for AI/ML, and these training jobs run this way. They have a checkpoint, and then they have 512 GPUs. And then on this GPU, they run calculation to the next checkpoint. And during this calculation, they do some calculation on their GPUs and exchange data across themselves, and then they do a little bit more calculations till they reach the next checkpoint. Checkpoint is just when application decides that it's checkpoint. And then they store the next checkpoint and continue further. So if one of the pods failed during the calculation between one checkpoint and another checkpoint, all other pods are just doing empty work, because this work, they will try to exchange data, and there is no data on this pod, and this step doesn't make sense. So they need to return to the previous checkpoint. And what we've been doing for training job, we were saying, OK, if one pod failed, we will scratch the whole job, unallocate all the GPUs, 520 GPUs, create new pods, allocate all those GPUs again, and schedule them, and then start from previous checkpoint. And we calculated millions of dollars wasted on single restart. Not a single, over a month, calculating number of restarts needed, and the millions of dollars wasted. There are calculations in cap justification. So this job will be implemented easily with restart all containers. So now sidecar orchestrator can exit and say, restart my whole pod from previous checkpoint, and everything will be working again. So now I have a few minutes to talk about future directions. And again, I wanted to emphasize the prioritization, how it happens. All the time, like we have many feature requests, and we're doing some small feature and cleanups and bug fixes. It's all given, and we want Kubernetes to be very reliable. For the new features, though, we quite protective because everything working for people, and we don't want to break anybody. So we need a lot of motivation to do new features. And right now, motivation is mostly coming from the fact that hardware is extremely expensive now. So all this like GPUs and like TPUs that allocated in major chunks, they are very expensive and needs to have a lot of attention. So we have a lot of improvements to utilize them properly. So DRA, Dynamic Resource Allocation, tells us how to allocate those devices. We try to do pods more dynamic, like restarting them, changes the size and shape of it. It's all also contributing to reusing the same resources without reallocating. We provide a swap memory support for less kills and more reliable execution of containers. And then we do some faster startup and other improvements. And all of that educated by AI/ML priorities. But I wanted to emphasize that it's educated by AI/ML priorities, but it also contributes to all other workloads. So as I talked about restart all containers feature, it's bumped in priority by the AI/ML training jobs, but it enabled at least 2 or 3 scenarios from the past, which people requested from us, and people wanted that implemented. So when we implement something for AI/ML, it also we never implemented just for AI/ML. Nothing works just for AI/ML. Even DRA, like we talking about DRA as something for accelerators, but in fact, we're working on DRA for CPU and memory, and this DRA for CPU and memory is very useful for Slurm-like application, like HPC applications using a lot of CPU, because now we can express via DRA what type of CPUs we have and what type of memory we have and how to allocate efficiently among those CPUs and memory NUMA slots. So yeah, that is working great. And how to get involved, as Peter said, wranglers are very helpful for us, and we encourage you to help us wrangle caps. You will learn a lot how a release process works and also what features we build. And also there are many other ways to participate. I think the most important for me is when people come and tell feedback, even like if they think that it's trivial, like obvious how things work for them. It's not obvious for everybody. Like I really like feedback in form like, oh, I told you 100 times that I need this feature. No, tell me 101st time, and maybe that will click with other features we have, and like it will be implemented as a bigger bundle. So this kind of feedback is very important, and we really appreciate it. But there are lots of work in SIG Node. If you want to get involved, please join us. And yeah, this is a way how to get involved, some links. And with that, thank you. If you have questions, there is a microphone, but if you don't, we'll be in the hallway for a couple minutes.
Hello, I have a simple question. I'd like to know the progress of the checkpoint restore working group. The working group is established recently, but I cannot hear any progress of it.
Yeah, so it like the PR to create the checkpoint restore working group merged last week. We like literally yesterday created the mailing list. So it's like, it's brand new, it's coming. I'm hoping it'll get started more in earnest as the new year starts, but probably at least for the next, over the next months, we'll be ramping up. So there's a mailing list now, you can join that, and we'll start to have meetings soon. Yeah, and there are individual solutions like on this KubeCon, there is a talk from somebody from Google about pod snapshotting. It's kind of same vibe of checkpoint restore. You can listen to this talk, but what we want in upstream in SIG Node is to unify it and create a common API. So it's not an individual vendor solution. It will be like API for everybody. Thank you, everyone.